Finally, in this video, we're going to discuss a very interesting class of quantum phenomena that appear in the presence of slow or so-called adiabatic time-dependent perturbations. And such adiabatic perturbations give rise to a very elegant mathematical structure, and in particular to so-called geometric Berry phase that we're going to derive. This Berry phase was discovered theoretically by Sir Michael Berry in this paper published in 1984 in the Proceedings of the Royal Society of London. And this is a really very well written and elegant paper. And actually, even though it's a research level paper, which in all likelihood may lead to a Nobel Prize for Sir Michael Berry, you are well equipped to actually understand everything in this paper. So both the derivation and the final results, because it requires nothing but the basic knowledge of single particle quantum mechanics and Schrödinger equation. So we're going to reproduce part of the derivation in today's lecture in this part. Of course, if you want to know more details, I would like to refer you to the original paper, which again is very well written. So the problem that Sir Michael Berry considered was, in retrospect, a very simple problem. So basically, it was the canonical Schrödinger equation with some time-dependent Hamiltonian, and he assumed two things. He looked into adiabatic perturbation, that is to say that the time dependence in h of t is assumed to be slow. What it means precisely we are going to define in the next few slides, but at this stage let's just leave it at that. So we have some very slowly changing Hamiltonian. And also let's assume that the Hamiltonian returns to itself after a certain period, let me call it capital T. So basically we have a periodic in time slow perturbation. And the question that he asked is what happens with the wave function as we get to this moment of time capital T. So what is the wave function at the final moment of time? So, and it turned out that, as we will see, so that this wave function has a very interesting contribution, sort of topological or geometric contributions. There are various descriptions of it that appear in the literature that was completely counterintuitive, and that takes some time to digest even after derivation. So now let me formulate the problem that he solved more precisely and proceed to the actual solution of the problem and to the formulation of this theory of the Berry phase. So let's imagine that we have a Hamiltonian that depends on a parameter lambda. Okay, so this could be anything. For example, it can be a magnetic field, or it can be some parameters of a harmonic oscillator, let's say the frequency, or something else. So whatever you want to think about. So let's have we have some set of parameters lambda, and we combine those parameters in a vector. So in principle, it could be more than one parameter, and we just construct sort of a vector in the parameter space, which doesn't have to be three-dimensional. But let me just, for the sake of simplicity, let me imagine that I have a three-dimensional parameter space. So let's say this is going to be lambda x, or lambda 1, lambda 2, lambda 3. Okay. And let me consider the situation where this parameter lambda is changing in time. So for example, again, it can be a magnetic field that is changing. And also let me consider the situation where after a certain period of time capital T, so the parameter returns to the original point. So if this is my parameter space, so basically what I'm talking about a slow evolution of this lambda such that it starts in a certain point and returns to the same point after time capital T. So, and as I advertised in the previous slide, so what I want to know is what happens with the wave function. So I have some initial condition for the wave function, and so the Hamiltonian after this period capital T returns to itself. So, but the wave function does not necessarily have to return to itself. So, and the question that we're interested in is what happens with this wave function. As a first step in this derivation, let me define precisely what I mean by a slow or adiabatic perturbation. So what does it actually mean that the Hamiltonian is changing slowly with time? And to provide this definition, let me formulate an eigenvalue problem, instantaneous eigenvalue problem for the Hamiltonian. So the Hamiltonian itself is changing with time, so there is no reason for us to write a stationary Schrödinger equation, but nevertheless, mathematically, it is well defined. So we can consider at any moment of time t, we can consider an eigenvalue problem for this h of t, and we can find a set of eigenfunctions and the corresponding eigenvalues, which I denote as e sub n of t. So for the sake of simplicity, let me actually assume that the spectrum of the Hamiltonian is discrete. So I have just a set of discrete levels. So n equals 0, n equals 1, etc. Also, let me assume that the initial condition for the wave function psi at t equals 0 is one of the eigenstates of my Hamiltonian at t equals 0. So and for the sake of concreteness, let me actually assume that it's the ground state. So n equals 0 at t equals 0. So by the way, it's not necessary really for the main conclusions of the derivation, but for the sake of concreteness, let me just be specific. Okay. Now, let us recall what we discussed actually in the previous lecture, in the previous part of this lecture, where we dealt with the opposite case of fast or sudden perturbations. So there we know that if we change the Hamiltonian very fast, the state, the initial state, which in this case is the ground state, would be sort of redistributed all over the place. So the particle after the quench, or after a fast sudden change, would exist in all possible eigenstates of the new Hamiltonian. And in some sense, it's natural to define a slow perturbation as the opposite to a sudden perturbation. That is to say that we will define a slow perturbation such that it does not induce transitions. So basically what happens here is, let's say this is the parameter lambda at t equals 0, and we have our initial state, the ground state with n equals 0. And as I change my lambda, so with time, so these energy levels start to move. So the energy levels really are these solutions to this eigenvalue problem, but the Hamiltonian is changing. And so the energy levels are moving, and in principle, also the explicit wave functions are changing. So, and what I can imagine happening is that the particle, which initially was sort of confined to the ground state, can in principle propagate to all other states. And this indeed will happen if the change in the Hamiltonian is fast enough. But if it is slow, and this will be the definition of slow, the state of the system would remain in the instantaneous ground state of my Hamiltonian. And also in this case, if I start from this point in the parameter space, return to the same point in the parameter space, so at the end of this periodic evolution, basically I require then the system would remain in the old ground state. And this will be my definition of a slow perturbation. So to mathematically define a precise condition for this to happen requires a little bit of work, and I provide this derivation in the supplementary material in the notes. And if you go through this derivation, you will see that the condition for this to happen, for the condition for having no transitions, is that the derivative of the Hamiltonian, which is an operator, and the matrix element of this dh dt between two states, let's say this ground state and, for example, the first excited state, this must be much smaller than the level spacing, the distance between these energy levels, divided by the typical time, the characteristic time at which the change in the Hamiltonian occurs. So this is the definition of, if you want, or the constraint that we have to satisfy in order for the perturbation to be slow. And one thing that we notice here is that, of course, if En minus E of 0 vanishes, that is, if the levels cross or if they come very close to one another, so this condition cannot be satisfied because we necessarily will induce transitions between these states. But if the gaps don't close, if the level spacing remains large enough, and if the change in the Hamiltonian is slow enough, so we can satisfy this condition, and to a good approximation we can assume that the system remains in the ground state during the evolution. So now we're in the position to actually derive this geometric Berry phase, and what it entails is essentially solving the Schrödinger equation, the time-dependent Schrödinger equation, under the assumption of the slow perturbation that does not induce transitions. So this is my Schrödinger equation. I'm just writing it down again. And here I'm basically requiring that psi of t remains proportional to the ground state. And the only thing I can have here is a phase, right? So because, well, the total number of particles is conserved, so therefore I cannot have here any coefficient whose absolute value is larger than 1, because it would imply that the probability to find the particle in this instantaneous ground state is larger than 1, and it doesn't make any sense. So, and I also require that, well, within my approximation there are no transitions, so the particle remains in the ground state. So there's basically only one possibility for this to happen, if this coefficient relating the wave function at time t and the instantaneous ground state is a pure phase, either for I phi of t or phi is a real function. So under these assumptions, what remains is to find this quantum phase. I mean, everything else we know, so this is really the remaining unknown in our adiabatic time-dependent problem. And if we plug in this form of the solution back into the Schrödinger equation and recall that by definition this 0t is the instantaneous eigenstate of the Hamiltonian, so we will simply get, so basically combining these two things will lead to the Schrödinger equation in this form. It will be IH d over dt of psi of t in this form is equal to the energy of the ground state, which is time dependent in this case because the energies are moving around, at psi of t. Okay, and well, so this is no longer an operator, actually. This is just a function. And naively, you may sort of assume that there exists a simple solution to this problem where phi would be equal to sort of a generalization of the usual quantum phase that appears even in the time-independent problem. So we could naively just write it as minus 1 over h bar, an integral from 0 to t, e naught of t prime dt prime. So again, if the Hamiltonian were not to depend on time, that is in this picture would mean that basically lambda is just a point which stays there. So I would just get the quantum phase being either by I minus I over h bar energy times time, which is the usual quantum phase that appears in stationary quantum mechanics. So here, instead, I may just go ahead and integrate from 0 to t. Well, it turns out, however, that this is not entirely correct, and there exists an important contribution which appears in, well, to this quantum phase. And let me write this contribution as gamma. And this additional phase gamma that we will derive in a second is exactly what is called the Berry phase. So this is our main quantity of interest. While the first part is sort of the usual dynamical phase. It's actually called dynamical phase. Let me denote it as theta with the subscript d, and this is called dynamical phase. If we plug in now back, basically this expression for the phase back into the Schrödinger equation, we're going to get, in the left-hand side, we're going to get the following terms. So there is going to be derivative of e to the power I theta, e to the power I gamma, and there will be the instantaneous ground state, 0t. And the right-hand side will remain the same. So and here we have the time derivative, which is going to act on three terms. So they're going to be three contributions in the left-hand side. So the first contribution, essentially by construction, is going to cancel out the right-hand side. So if we differentiate this exponential, so let me just write it down. It's going to be I h bar times I theta d dot times psi, and this theta d dot is the derivative of this integral, which will just pull out the value of the energy. So this whole thing is going to be equal to the energy as a function of time, which will be cancelled by the same term in the right hand side. So there's going to be also another term here, so it's going to be I h bar I gamma dot times psi. And finally, there's going to be a derivative of the wave function itself. So the eigenstates are changing. So the Hamiltonian is changing, and so do the eigenstates. So therefore, there's going to be another term. So let me write it plus I h bar e to the power I theta plus gamma. Here we're going to have the derivative of this guy. And the right hand side is E naught times psi, which, as I already mentioned, is going to be cancelled precisely by the first term in the left-hand side. That's why we introduced this dynamical phase in the first place. And now what remains is simply to balance out these two terms. And as you can see, a lot of things cancel out. So the Planck constant cancels out. So the phase factors in this term are going to be cancelled by the corresponding phase factors in this wave function. So this goes away, and I times I is equal to -1. And so what we can write is the following. So let's say in the left-hand side we're going to have a gamma dot. The wave function, the ground state wave function, is equal basically to this guy, I d over dt, 0t. So finally, what we can do here, we can take advantage of the fact that we have normalized states. So the number of particles is conserved, and therefore, and our particles exist in this ground state. Therefore, this bracket product of this instantaneous ground state with itself is equal to 1. And so if we multiply this equation from the left by bra vector 0t, so we're going to have simply 1 in the left-hand side, and we're going to have 0t d over dt 0t in the right-hand side. So therefore, what we can do, we can write the Berry phase, well, this Berry phase gamma at the time t as an integral from 0 to capital T. So this is the time that it takes the particle, well, the system to return to the original Hamiltonian. Under this integral, we're going to have 0t d over dt 0t dt. So it's an integral over time. So we get this interesting term, which is the Berry phase, and as we shall discuss in the last slide, so this term has a very interesting geometric interpretation. That's why it's called a geometric phase. To see this, let us recall the definition of these eigenstates, 0t. So those are the instantaneous eigenstates of the Hamiltonian, but per our assumption, so the Hamiltonian depends on time only through the parameter lambda, this vector parameter lambda. So instead of writing these guys as being parameterized by t, we can as well parameterize them by this parameter lambda in this parameter space here. And if we do so, we can transform this integral over time into an integral over lambda in this parameter space. And this would acquire a very curious, as I said, geometric interpretation. So almost the last step here is to perform a change of variables and to go from an integral over time to an integral over lambda. And this can be done by simply writing, so here this d over dt can be written, so this is the identity, it can be written as d lambda over dt, d over d lambda, okay? And on the other hand, when this guy is going to multiply this differential, so we can simply replace this product by d lambda. And so another way to write this Berry phase, so let me present it here. So gamma can be written as an integral, and now this integral will go actually around this loop in this parameter space. So it's going to be a closed integral. So let's say if this contour, we call it C, so it's going to be basically encircling the C, and here we're going to have 0 lambda d over d lambda, 0 lambda d lambda. Okay, so this is just another way to write essentially the same quantity, but the time is completely gone from our description, even though we started with a time-dependent problem. So here time is not essential anymore. So another thing we can do, we can introduce simply a new notation. Let me call it a vector notation. A is a function of lambda, which is by definition going to be this guy. And so in these notations, we can see that the Berry phase is nothing but a circulation of this potential, if we want, A of lambda, around this contour. Okay. So another thing that we can do here, we can take advantage of certain identities from the vector analysis, hopefully familiar to some of you who have studied the theory of electromagnetism. Namely, we can define the curl of this vector A. So let's define the curl of A, curl with respect to this lambda, and let me call it B of lambda. And if we do so, this Berry phase gamma can be rewritten as a flux of this, I will call it fictitious magnetic field, through the area enclosed by this loop that corresponds to this quantum evolution. Okay, so essentially, well, it's very complicated, but so those of you who, again, who are familiar with the theory of electromagnetism may remember that to describe magnetic field in real space, it's oftentimes convenient to introduce a vector potential such that the curl of this vector potential is the magnetic field. And so here, instead of the real space, we have this sort of fictitious parameter space, which does not have to be a real space. It can be something else. It can be just a set of parameters in our problem. And what we found is that the quantal phase that will be acquired by the wave function as a result of this evolution is essentially a flux of some fictitious magnetic field that exists in this model. Okay, so by the way, notice that even though we started with the time-dependent problem, this B of lambda and the corresponding vector potential A can be calculated by themselves. So if we just have a Hamiltonian which depends on lambda, whether or not it depends on time is a separate matter, we can just go ahead and calculate these properties. And so what we may think about is that when we have a quantum system which is parameterized by some parameter lambda, so there exists an internal, in some sense, fictitious magnetic field in this parameter space. And so it exists whether or not we perform quantum evolution, but if we do perform quantum evolution, and if we have this sort of periodic time-dependent perturbation, so the quantum phase that will be acquired by the particle is going to be basically the flux of this magnetic field, if you want, through this area enclosed by this loop. And that's why it's called a geometric phase. Sometimes it's also called topological phase. It's a very non-trivial concept. So, I mean, first of all, it was not discovered in the early days of quantum mechanics. It was discovered only in the 80s. And furthermore, only now, and this is basically the subject of current research, we're starting to understand the true importance of this Berry phase. And one of the recent discoveries that you might have heard about is so-called topological insulators. So sadly, I didn't have time to talk about these quite amazing discoveries, but I just wanted to mention them in passing to sort of emphasize that this is not just a pure mathematical construct, which is sort of elegant by itself, but also it does have important physical applications, and this is the subject of current research. So the final thing I'm going to mention here, sort of concluding this technical discussion, is that unlike the magnetic field in real space, which does not have sources or sinks, so there are no monopoles as we know, so the divergence of the magnetic field is zero. So this fictitious magnetic field actually can have sources. And these sources are, well, some sort of monopoles in this parameter space correspond to the degeneracies in the spectrum of the problem. So what it actually means is, and this is one of the results understood by Berry in his original paper, is that if we have some values, some special values of parameter lambda, let's say call it lambda star, such that there may exist two wave functions with the same energy, so basically the energy levels cross. So then these points, let's say this point, serve as sources or monopoles of this magnetic field. So in this parameter space, this is also a very interesting result. Well, it's a very interesting subject. I could definitely talk more about it. It's a very exciting field, but I feel that I probably should stop here because I've been talking for 25 minutes now in this last part of the last lecture. And I just would like to thank you very much for your attention. I hope that this lecture and in general the course were interesting and useful, at least some parts of it. And I wish you all the best. Thank you very much.